I'm Tyler Harder. I'm from the University of Wisconsin-Madison, where I'm advised by Professors Andre Arapachi-Dussault and Ramzi Arapachi-Dussault. And this is a joint work with our friends at Facebook, Dhruba Bordekar, Sayang Duang, Amitanand Ayer, and Lian Tang. So today I'm going to be presenting an analysis of HDFS under HBase, a Facebook messages case study. We think messages and the underlying stack is interesting to study for 3 reasons. First, it represents an important class of applications. In particular, messages is a backend for cell phone texts, chats, and emails. More broadly, the messages stack represents the HBase over HDFS design, where we have a distributed database built on top of a distributed file system. This kind of architecture is common in Facebook and other companies, and a similar stack is used within Google, Bigtable over GFS. Even more broadly, storage systems are rarely built from scratch today, and we think that by studying the messages stack, we can learn lessons about layered storage in general. So let's start by chatting about how we might build a distributed application like messages. We start with many machines, each of which has many disks, and the challenge is how can we use these resources to store messages for the user? One option would be to use all these hardware resources directly. While that would yield some very specialized performance, it would come at a very high development cost. So instead, messages uses a simple put and get API of HBase, which begs the question, how should we build a distributed database? Should HBase manage disks directly, or should it focus on higher level database logic? Managing hardware failures is challenging, so HBase stores all its data in HDFS, which can then handle machine failures and disk failures by replicating its data across many machines. But even HDFS does not do all the work itself. Instead, for disk layout, it leaves those details to many local file systems, one per each disk. This stack has some obvious advantages. Each layer can build on the previous one, so each layer should be simple and therefore have fewer bugs. This will lower the development costs since many of these lower layers have been built for other purposes. And finally, you can take advantage of code sharing. If the MapReduce people improve HDFS, maybe the HBase users can also benefit. However, there's a few questions we should address. Is all this layering free in terms of performance? Second, if we integrate the layers and they're more aware of their stacking, can we get better performance? And then finally, what should the hardware layers look like? Do we want a single flat layer or tiered storage? So I'm going to briefly go over our methodology for addressing these questions, give an HBase background, and then dive into some results. So here's the stack again. And what we first do is we instrument HDFS so we can collect HDFS traces at the interface between HBase and HDFS. We do this with a new tracing framework we built, the Hadoop Trace File System. This is open source and distributed along with Facebook's distribution of Hadoop. This tracing framework collects details about individual read and write requests, such as offsets and lengths. Within Facebook, requests are often mirrored to 2 clusters, a production cluster which serves the user, and a shadow cluster which is used to test new versions of the software. We did our tracing on 9 randomly chosen machines in a shadow cluster so that we could study the real workload without imposing tracing overheads on real users. We collected our traces for 8 days and collected over 70 terabytes of HDFS I/O. Now we take these traces and we do 2 things. First, we feed them to an analysis pipeline that allows us to characterize the workload. This suggests different ways that the stack could improve. To evaluate the improvements, we then feed the traces to a 2-level simulator. First, the traces go into a simulation of HBase and HDFS, and that, via a knowledge of replication, infers what the local file system traces might look like if we had collected them. Then we take these inferred local file system traces and we feed that to a model of local storage. This allows us to ask a bunch of what-if questions, such as what if we had more disks or used a different caching policy? So before I can tell you what we found in these traces, I need to give you a brief background about how HBase uses HDFS. So HBase has 4 different activities which cause HDFS I/O, and I'm going to walk you through these. On the right of this slide, you see at the top HBase memory, which contains this memtable data structure containing key and value pairs. And then also on the bottom, you have all these HDFS files. So let's say you get a put of a key value. The first thing you're going to do is add that to the memtable and write it to the log for durability. After many puts, the memtable becomes full, and you have to flush it to a data file. After many such flushes, you may have many data files, and whenever you receive a GET request, the GET request will have to check potentially several of these to get the latest version of that key and value. Now, if you get too many files, this GET can be expensive, so what we do is we merge sort the small data files into one big data file. HBase calls that a compaction. So of these 4 activities, 2 are crucial, flushing and foreground reads. Without those, HBase and messages couldn't operate. And the other two are overheads. While logging is useful for crash recovery, it's not needed for normal operation. And compaction, while it improves performance of gets, is not required for correctness. So for the rest of the talk, I'm going to share some findings from these workloads and then simulate both hardware changes and software changes and see how we can build the best storage for this stack. We'll ask 3 analysis questions. First, at each layer of the stack, what activities are doing reads and writes and how much data is being touched? Second, how large are created files? And third, what are the patterns between reads, if any? Let's ask the first question. So what I'm going to show on this slide is the amount of I/O done on each layer represented by the size of these bars. I'm going to also break these bars down by the portion of reads and the portion of writes. So what this first portion shows is that of the baseline HDFS I/O, there's about 45 terabytes of I/O happening over our trace window. Furthermore, the dark purple section representing reads shows that 99% of this baseline I/O is reads. This makes sense because if you imagine you're messaging with somebody occasionally, you might have to view dozens of previous messages for every new message that you write. So there's only 1% writes at this level. Now let's include some compaction and overheads though. Compaction and logging overheads. Here we see 2 things. First, these overheads are significant, and second, they're dominated by writes. This brings up the total HDFS I/O write percentage to 21%. Now when you're writing an HDFS file, it's triply replicated, so every byte you write will end up to 3 write bytes in local file systems. This is not so for reads. You can just read 1 read from a local file system replica when you want to read from HDFS. So this brings up the local file system number of writes to 45% because we have here replicas 1, 2, and 3. Now not all this local file system I/O is actually going to hit disk because we have a local cache. So this third plot shows the disk I/O as we determined via simulation, and we see that the reads shrink due to caching, bringing the write percentage up to 64%. So our first finding is that layers greatly amplify writes. In this case, we had a very read-dominated workload with only 1% writes, and then finally at the disk level, that blew up to 64%. So regardless of how read-heavy your workload is, in this kind of stack, you really have to optimize for writes. This plot is similar to the last one, but now instead of looking at I/O, we're looking at the size of the data set that was touched. So you can see several things here. First, we have the purple, which is data which is only read, the light blue, which is data which is only written, and then the shaded regions represent portions of the data set, which is both. And you see that the red data is much smaller portion of the bar than the reads in the previous plot. And that's because a lot of these reads are concentrated on a small subset of the database. Another thing we see here is that there's very little overlap between read data and written data, which is our second conclusion. And that's because logs tend to be written but not read unless you crash. And a lot of the compactions that are doing writing are compacting older data, which doesn't need to be read as often as fresh data. Now I'd like to draw your attention to this bottom bar. And we're going to compare this bar, which represents data that was touched at the file system level, to data which was sitting in the file system but not touched. So data that wasn't touched at all is shown up as cold data here. And what we see is 2 things. The data set is very large and very cold. 2/3 of this 120 terabyte data set is never touched at all. Our next question is, how large are the created files? We can show that with a simple CDF of file size for the created files, and I'll just highlight a few points on here. First, half of the files are smaller than 750 kilobytes, and 90% are smaller than 6.3 megabytes. Therefore, our fourth conclusion is that files are much smaller than has been traditional for HDFS. HDFS was previously built for MapReduce, which often operated on multi-gigabyte files. And the fact that we have smaller files means there's going to be a higher metadata to data ratio, and that raises questions about whether it makes sense to have all the metadata stored by a single name node. Our final question is, what are the patterns between read requests, if any? And we're going to look at 3 patterns: temporal locality, are reads near each other with respect to time, spatial locality, and sequentiality. So let's talk about temporal locality. We can think of temporal locality in terms of caching. So in this plot, I have along the y-axis a hit rate, and I'm counting a read as a hit if it overlaps at all with data that's in the cache. And along the x-axis, we have the amount of time that data resides in the cache. So if you keep data in the cache for longer after a read, your hit rate can only go up, which is why this line only rises. Let me identify a few points on here. First, we see that if you cache data for half an hour after it's read, we get a 25% hit rate. So 25% of the reads are to data that was read within the last 30 minutes. Half of the reads are to data which was read in the last 2.5 hours, and about 75% are to data that was read a little less than a week ago. Thus, these reads are near each other with respect to time. Put otherwise, we see that there's very high temporal locality in this workload. So we can go back to this picture, and now we can talk about sequentiality by adding some more details. In particular, instead of just talking about caching now, we can talk about prefetching, which is what this green line here represents. So the previous red line just showed 0 prefetch, but now for every read, we want to see what would happen if we prefetched 1 kilobyte before and 1 kilobyte after every request. So since we have prefetching, the hit rates can only be higher, as you can see. Now the interesting point on this plot is the 1 minute point. And what we see is that only 25% of the reads were preceded by an adjacent read within the last 1 minute. That means that at most 25% of the reads are sequential and over 75% are random. This again represents a deviation from the traditional HDFS workload where you had large streaming writes. We can add another detail in here to talk about spatial locality. So now in addition to the 1 kilobyte prefetch, I'm going to show what would happen if we had a 64 kilobyte prefetch. And what's interesting about this line is that it's so very close to the 1 kilobyte prefetch. And what that means is that, except for sequentiality, reads tend to be very distant from each other with respect to space. In other words, spatial locality is low. Perhaps part of the reason is that the application tends to read in fairly large block sizes, so it's already prefetching itself. So additional prefetching at this layer of the stack would not be useful. So now that we've went over all of these findings from the workload, I'm going to walk through how these apply to both hardware and software. So let's talk about hardware first. Let's say we want to build a hardware storage layer. We could do it with a single layer of flat disks, a single layer of pure storage, or we could use a hybrid. What does our workload say about this? Well, we saw that there were very random reads, which is going to be bad for disk. Also, we saw that many of the reads were repeats to the same small portion of the data set. If you have a lot of hot data, maybe it should be in a faster medium. And finally, there were many small files. All these things combine to suggest that a pure disk system, as is used now, is probably not the ideal hardware. What about pure flash? Well, we saw that the data set was very large and very cold, and storing all of this in flash would probably cost about $10,000 per machine, given current market prices. So also pure flash is not a good option. Therefore, by the process of elimination, we should have hybrid storage. Okay, so let's be a little bit more rigorous about this now. What we really want to do is we want to try different combinations of different amounts of flash and RAM and disk and see what is the most cost effective. So I explore 36 points in this space with 3 levels of disk, 3 levels of RAM, and then either no flash or an SSD, which is 60, 120, or 240 GB. So for each of these, it's easy to compute the cost based on the assumptions in the cost column of this table. And then for the performance, we determine that via our trace-driven simulation. In particular, we tell our simulator how much of each type of hardware we have, and then we also feed our simulator these performance assumptions which you see here. When we do the simulation, we use the RAM and flash together as a single LRU cache. We use a no-write allocate policy, and we have exclusive tiers. In other words, you can never have the same block of data in flash and RAM at the same time. So for each of these, we get the cost and performance, which we're going to plot along the x-axis and y-axis of this plot, respectively. And we're going to talk about how we can move between different points in this plot. And in particular, we're going to talk about how an upgrade can decrease latency for an increase in cost. A good upgrade will be one that greatly decreases latency for a small cost increase, and a bad upgrade will be one where you pay a lot for only a small latency decrease. So let's talk about upgrading disks. Here I've highlighted all the machines with exactly 10 disks, and what I'm going to do is I'm going to draw a line from these machines to the 15 disk machines that are otherwise equivalent. So let's draw those lines. And we see that sometimes the lines are fairly steep, so it's a good improvement. Most of the time, the lines are relatively flat, meaning that you can get some performance gain, but it's going to cost you a lot of money. If we upgrade to 20 disks, we see that most of these lines are extremely flat. That means buying disks for the sake of performance is throwing your money away at this point. Of course, you might have to buy more disks to hold the large data set, but you shouldn't buy it for performance. So what about buying more RAM? Here are the points with 10 gigabytes of RAM, and upgrading to 30 gigabytes, we see that the lines are often quite steep, so this is a good gain. However, some of the lines are also flat, so whether or not you should buy RAM depends on where you already are within this three-dimensional space. Upgrading to 100 gigabytes, again, is sometimes useful and sometimes not so much. So we see that while upgrading RAM can be useful, it depends. So it's better than disk, but it's still not great. So let's look at flash now instead. Here are all the machines with no flash. As you notice, these are at the top of the plot. So the no flash machines are the slow machines. If we throw in a 60 gigabyte SSD, however, we see that the lines are very steep and very long. So for a very small increase in cost, you can easily double performance. Upgrading to 120 continues to have good gains, the lines are steep, and even buying a 240 GB SSD is quite useful. So upgrading flash is a very cost-effective way to improve performance. Another way we can think about these data points is we can talk about the ones that are Pareto optimal and exclude the others. In other words, if there's any point that's both slower and more expensive than alternative, we'll exclude that, and we're left with these. So I've put a line through this curve. And what's interesting about these Pareto optimal points on this curve is that they mostly fall into two categories. First, these green machines have the maximum amount of flash, and these purple ones have the minimum amount of RAM and disks. So what does that mean? That means that if you want to get better performance, you shouldn't buy more RAM or disk unless you've already maxed out your flash, at least within the space that we explore. So we've seen then that it makes sense to have two hardware layers, and now we're going to move on to talk about software layers. In particular, we're going to see how we can integrate the layers to get better performance. So what does our workload analysis from earlier suggest we should do with the software layers? Well, the main thing we saw is that writes are greatly amplified, from just 1% to 64% at disk. So we really need to optimize writes, not only because they're so prevalent, but because the writes often have associated network I/O, which is additionally expensive. So which writes should we optimize? Our analysis tells us that too. 61% of the writes were for compaction, and 36% were for logging. So I'm now going to share two techniques with you, one for improving compaction and one for improving logging. So let's go to a picture of some worker machines here. And as you can see, there's 3 physical machines, and each is running 2 servers, an HBase worker and an HDFS worker. The 3 lines coming out of the middle machine are representative of the 3-way replication provided by HDFS. And the problem here is that 2 of these lines are crossing machine boundaries, and that means that those big red lines are network I/O. A common way to avoid sending a lot of data over the network is to ship the computation to the data instead of shipping the data over the network. So that's what represented by these small dashed lines, such computation being shipped. And we can actually use this technique for compaction. So instead of having the one machine read the small files, compact them, and then send them over the network, we could send a do compaction command to each of the replicas of the data. We can do this because compaction is just merge sort, so it's deterministic, and if each replica applies it, they'll all come up with the same result. So then the primary replica can read the files and do compaction as normal, and then each of the other replicas can apply this compaction function to get the new data. So let's evaluate this via simulation. In this plot, we have cache size along the x-axis, and along the y-axis, we have read I/O in terabytes. So as you can see here, the normal network I/O is 3.5 terabytes per machine over the tracing period, and you can see it doesn't vary with cache size. When we switch to local compaction, that drops by 62%, so this is quite useful. However, this is not completely free because disk I/O here, which is a function of cache size, is going to go up by a similar amount. In fact, we even see that for a 30 gigabyte cache, the 2.2 terabyte reduction in network I/O translates to a 2.4 increase in disk I/O. And that's because these compaction reads are usually cache misses, and also they tend to pollute the cache. However, if you have a very big cache, we can actually get a 2.2 to 2.1 trade-off. Regardless of where we are in this space, this is a great trade-off because Facebook engineers tell me that they end up spending a lot more money on their network hardware than on disks. So if we can trade network I/O for disk I/O, that's a great trade-off. So I've shown in this picture how we can improve compaction writes, and now I'm going to show you another approach that we can do for improving the performance of logging writes. So because of this 3-way replication, a typical HDFS worker is going to be receiving logs from 3 different HBase workers. And because each of these logs are independent HDFS files, those files are going to end up on different disks for the replicas for this HDFS worker. So there's going to be a lot more seeking than would be strictly necessary. As an alternative, HDFS could expose a special logging API such that whenever something is marked as an incoming log file, it could merge those streams on a single dedicated disk. So let's simulate this now and see the impact on performance. So in this plot, we have the number of disks along the x-axis, and along the y-axis, we have the latency of different types of disk requests. This first line, 2 lines show the latency of log writes, both with and without combined logging. And what we see is that switching to combined logging makes log writes 6 times faster, because we have this dedicated disk and it's all sequential I/O. But now we have 1 fewer disk for compaction and reads. So let's see how that is affected. Surprisingly, compaction is also faster, even though it has 1 fewer disks. This is because it no longer has to compete with logging. And even the foreground reads are improved by 3%. Now, the way the stack is currently built, if you do a put, it won't block until the data is durably on disk. It only blocks until the data is replicated in RAM on the 3 replicas. So combined logging is only going to give us a 3% benefit now. However, where combined logging would be really useful is if we ever wanted to make a stronger guarantee, namely that a put doesn't return until data is really durable. In that case, combined logging could make that guarantee 6 times cheaper. So now I'd like to conclude by saying that for hardware simulation, we really want to have multiple layers of the stack where we can keep hotter data in flash and colder data in disk. And then for software simulation, we can use better integration to really overcome some of the overheads of layering. So to conclude, I'd like to see how some of these ideas relate to common ideas in the storage community. So GFS was built on assumptions about the workload, and it was optimized around those assumptions. The original GFS paper said that high sustained bandwidth is more important than low latency, and multi-gigabyte files are the common case. What we see for messages, though, is that the workload is the exact opposite. Half of the files are smaller than 750 kilobytes, and over 75% of reads are random. This raises questions about how HDFS should evolve. For instance, now that we have all these small files, which have a fixed amount of metadata, we have a much higher metadata to data ratio. Does it make sense to concentrate this all on a single machine, or is it perhaps time to distribute metadata across many machines? Next, Dijkstra said that layering proved to be vital for the verification and logical soundness of the THE operating system. And while that's certainly true, we find that layering does not come for free. In particular, over half of the network I/O related to replication we found to be an unnecessary side effect of layering. Furthermore, combining these layers with logging meant that logs writing was 6 times slower than it really needed to be. Another finding is that the layers tend to amplify writes, often multiplicatively. What I mean by multiplicatively is that we observed a 10 times logging overhead, which combined with a 3 times replication overhead to produce a 30 times replicated log overhead. And you see a similar thing for compaction. Fortunately, it's not all bad news. We found that if you put a little bit of effort into better integrating layers, you can keep the simplicity of layers while greatly overcoming a lot of these normal costs that you would face. In particular, we found that local compaction via function shipping can really help you reduce your network I/O, and combined logging can greatly help you reduce disk seeks. Finally, Jim Gray predicted that tape is dead, disk is tape, and flash is disk. And what we've really seen is 2 trends. One is that flash costs have greatly plummeted, like Gray predicted, but the size of data has also exploded. And how do we balance these 2 trends? We find that for messages, the balance means that flash is actually a very poor disk replacement. And that's because the data is very large and mostly cold. You can't necessarily put it on very cold storage because you still have to search for this, but it's not going to be accessed very often either. And using pure flash to store all this data would cost over $10,000 per machine. However, there's still a story for flash. We find that adding just a small SSD is a very good way to double performance for only a marginal cost increase. Thank you. Any questions?
Hi, Bill Belowski from Microsoft Research. So one of your main conclusions is that file sizes are small, and you back that up by looking at the median file size. In a number of pieces of research that we've published, we found that file size distributions are heavy-tailed, and in particular, if you look at the mean file size, we found them, say, 3 orders of magnitude larger than median file sizes in an admittedly very different setting. And to a large extent, that's what really matters, right? It's where the byte, what size. So did you look at mean file size?
Yeah, we did have some numbers in the paper. I don't have them off the top of my head. And my thought is that, so one of the patterns we observed is that a lot of these small files they're flushed out, but they quickly get compacted into bigger files. So the concern is not so much that we have all this metadata that's hard to store in memory, but that every time you create a file, you have metadata operations. And in that sense, it's like the pure number of files that's going to matter, because you have to, the name node has to perform metadata operations for each of those. So I think, yeah, I think that could be consistent with what you're saying.
Okay, thanks.
Hi, Brad Moore, HP Labs. So I like this piece of work. With regards to the function shipping idea, I think you're making an assumption about where the replicas of each of the data chunks end up. So in a big system, you're going to move your data, your chunks. You're going to distribute your chunks across all of the servers, because that gets you better recovery time. Mm-hmm. And in the system you described, I have to put all of the replicas for a single thing that I want to compact without doing network I/O in the same place, mm-hmm. which is going to make your recovery time a lot worse when you have to replicate all of that data to another node. Mm-hmm. Have you thought about that, or?
Yeah, I guess you're right. So like currently the replica placement policy is pluggable, and you would have to plug something in that tends to group secondary replicas together. And they don't currently do that, but you certainly could. And wouldn't have to be perfect all the time, because if you occasionally are missing a piece of data, you could pull it in. In terms of recovery costs, we haven't done any simulations, but my thought is that you have many different regions where you also shard the data. And so you could balance across other dimensions instead of just these replicas. So I'm saying that the units of replication here for a given piece of data are relatively small. So I think it would be okay in terms of that. But we don't have any simulation numbers.
Okay, thanks.
Hi, Margot Seltzer from Harvard and Oracle. I really like the work. I like the methodology. I want to ask you about your first conclusion, though. So your first conclusion was GFS was designed for a fundamentally different workload. They're using it here, so therefore HDFS should evolve. And I guess my question is, that seems backwards. GFS and HDFS were designed for a specific workload. This is a very different workload. Shouldn't this use a different file system?
Yeah, it seems like perhaps. I mean, I think part of the thing is that Facebook has used HDFS for a lot of other things. So you have a lot of people with a lot of knowledge. So perhaps rather than using the best possible file system, this yields a lot of simplicity if you can kind of have a more uniform stack. So I think it's a trade-off there. But yeah, I think using a more specialized file system would definitely get better performance.
Michael Mixrow, University of California, Santa Cruz. I'm very fascinated with this work. It shows that layers are very good for layers are very convenient for designing large distributed systems. However, as you demonstrated, layers are not free. Regarding solutions to this layering problem, one solution that immediately comes to mind is there was a paper that came out in 1996 out in University of Washington called SPIN, where SPIN is an operating system that allowed applications to provide functions for certain OS tasks, such as scheduling and other things, to help alleviate some of this layering problem that have been cited about in literature as far back as Stonebreaker's work in 1981 on databases on top of OSs. So regarding solutions, do you think that for certain architectures for like HDFS, Hadoop, HBase, and other things that are constantly layered on top of each other, do you think that they should adopt a more extensible architecture, kind of like SPIN, or do you think that there should be a different approach to them?
That's interesting. I think I'm not very familiar with the SPIN work, but I think it would make sense to make things more extensible. And I guess the function shipping would be an example of that, because then the higher layers could define whichever functions they want to use, and that would be a form of extensibility. So yeah, I think, yeah, that makes sense.
Thank you.
Thank you.
Konstantin Shvachko from OneDisk. Interesting, very methodology. I was wondering where you get those small files, because the region size is equals in HBase to the size of the block, and here you have really small files. Looks like that you're having on the application level, very small tables?
I think the reason why the files are so small is that first you distribute the data across a bunch of different regions, and then you'll flush the data for each region at a given time. And when you flush it, that data is broken up into different column families. There's some more details in the paper on that. And you're going to flush each column family to a different thing. So when you break up your memory along both regions and column families, you have to write data in very small chunks.
Got it. Lots of
Yeah.
column files. And quick question about SSD. So it's used for this hot data or as a cache or both?
So we tried using it both as a write buffer and as a cache, and we found that probably the best solution is just using it as a simple read cache.
Thank you.
Just one last question. Do you have any plans to release the HDFS traces?
I would love to, but I feel like we'd have to jump through a lot of legal hoops, so I'm not trying to push in that direction, but maybe somebody could convince them.
We can thank Tyler again.
Thank you.